All right, so let's go ahead and finish out this week so we can get to week ending here. We're going to pick up where we left off last time, which was talking about these empirical formula problems, okay? So just to review empirical formula, what do I mean by this? Right, we said that if we have a covalent compound, the molecular formula, those subscripts can be anything, right? So we could have, for example, a molecular formula of C3H9. I'm using this word molecular formula. What does that mean when I'm saying molecule? What type of compound are we talking about here? Ionic or covalent? Covalent, right? And I can tell that by my formula. We got these two nonmetals here. Okay, so my molecular formula, those subscripts can be anything. There's no way to sort of predetermine just by looking at the periodic table like there was for ionic compounds. These covalent compounds, these numbers can be anything. All right, so that would be the molecular formula. If we simplify the molecular formula, we pull out any common factor that exists between those two subscripts. So in this case, CH3, I divided both of those values by 3. This is what we would call the empirical formula. Okay, and so why is that important? Because an empirical formula we can determine using an experiment called mass spec. Okay, and so that was that data that we were looking at before. All right, so that's our goal, is to look at some mass spec data and determine the empirical formula of a compound. All right, so going back, here was our mass spec data here. We have an unknown compound that contains 7.07% carbon and 92.93% selenium by mass. And we want to know what is the empirical formula for this compound. So to be clear, my formula here is going to be some amount of carbons. I just don't know how many. And some amount of seleniums. I just don't know how many. And that's our goal, is to figure out what X and Y are in this formula. Right? What is X and Y? That's what we're trying to figure out. What is our formula for our compound here? Okay? So what we're going to do first is we're going to take this percent by mass data here, and we're just going to assume we have a specific amount of that compound. And we could assume we had any amount, but the most convenient amount to use is 100 grams of that compound. Because if I have 100 grams and it's 7% by mass carbon, that means I have 7 grams of carbon. And if it's 92.93% selenium and I have 100 grams, that means I have 92.93 grams of selenium, right? So by making this assumption that my total amount that I'm working with is 100 grams, it makes my life a little bit easier in terms of the math of the problem. Okay, and then the next step here is to convert from grams to moles for each of these quantities. So I'm going to do two separate calculations. One converting from 7.07 grams of carbon into moles of carbon, and a second converting from 92.93 grams of selenium into moles of selenium. All right, and when we see grams and moles, what are we thinking? It's not, so Avogadro's is when we have atoms or molecules or some tiny, teeny, tiny thing. When we're dealing with the space of moles and mass, that's when we need our periodic table value, our molar mass. All right, so just going back to our periodic table here. Okay, again, I'll put down our goal here, grams to moles for each of these two elements. Okay, everybody take a second, see if we can't set this up here. I'm going to give you guys a head start, and then I'll go in and solve it. going to focus just on the carbon here. But remember, we got to take this value from our periodic table, our molar mass, and we're going to turn it into one of these conversion factors that we can actually use in our math here, where we say 12.0107 grams of carbon are in 1 mole of carbon. Right? That's our molar mass information from the periodic table. So then I'm going to start with my 7.07 grams of carbon, and I'm going to use my molar mass to convert to moles. Am I going to multiply or divide by that molar mass? I'm going to have to flip it, right? I need grams on the bottom. So 12.0107 grams of carbon, and moles of carbon are on top. Okay? So 0.5886. All right? So the nice thing about these empirical formula problems, and we'll see why here in a second, is that we actually don't have to worry about sig figs. Since at the end of the day, what we're getting at is this empirical formula. This is one where we don't actually really have to keep track of sig figs. So we're just going to take a few extra digits to work with here, all right? But I'm not going to go through my process of my sig figs like I normally do. Okay, and units-wise, grams cancel out, and so I'm left with moles of carbon. If we're going to do the selenium conversion, we're going to do the exact same, but we're going to use the molar mass of selenium, the 78.96 grams per mole. Okay, so let me just move back to the other page so I got a little bit more room to work with here. All right, I'm going to take my mass of selenium, the 92.93 grams of selenium. And again, divide by that molar mass from my periodic table, the 78.96 grams of selenium that are in 1 mole of selenium. Again, just that value from the periodic table. All right, and so this works out to be 1.1769. Again, just take some extra digits here. Moles of Se. All right, so I took my percent mass data here. I assumed I had 100 grams, so that would leave me with 7 grams of carbon and 93 grams of selenium. All right, and then I converted those values into moles using the molar mass of each element from our periodic table. Now, I can't just say that my formula is carbon 0.58864, selenium 1.1769. We can't have these fractions, these decimal numbers in our empirical formula, right? We have to have whole numbers, counting numbers, 1, 2, 3, 4, okay? So I'm not done quite yet, but believe it or not, in these numbers here, and unless you're like a master calculator brain, you can't really see just by looking at these numbers, but locked in these two numbers here is that magic ratio of carbons to seleniums in my empirical formula, okay? There's this special relationship between these two numbers, but it's really hard to see in this decimal form right here, okay? So what we're gonna do is this little trick that's gonna make it more obvious to us. We need these to be whole numbers, right? Well, a guaranteed way to make at least one of them a whole number is to divide both of them by whichever value is smaller, okay? So step 3 here, we're going to divide both by the smaller value. All right, so which one of these am I going to divide by? The 0.58 or the 1.17? Yeah, so I'm going to divide both of those numbers by that 0.58. And so let me show you what I mean real quick by it's going to guaranteed make one of them a whole number. When I take my 0.58864 moles of carbon and I divide that by 0.58864, what am I going to have? 1, right? And again, the whole goal is to turn these into whole numbers here. So now I have at least one of these as a whole number. Okay, I'm going to take that second value and divide it by that same 0.58864. Okay, and I'm actually going to copy and paste these numbers from my calculator so that I have even more decimal places than what I've written down on the board here. Okay, and this will come out to 1.9993 moles of selenium. All right, now because this is data that we're working with here, rarely, if ever, will it really come out perfectly to a whole number. But 1.9993 is really freaking close to what whole number? 2. Right? So this is telling me that for every 1 mole of carbon in this unknown compound, there are 2 moles of selenium. And that is, of course, what my empirical formula is telling me. Right? So what this is telling me is that for every 1 carbon, C1, there are 2 seleniums. Okay, the 1 we don't actually bother writing in our formula here, and the 2, again, I got from my 2 moles of selenium, is why that appears in my empirical formula. All right, so there was this 1-to-2 ratio of 0.588 and 1.1769, but you can't really see that, right? That's very difficult to see just by looking at those numbers with all their decimal places. We can make it way more obvious if we take both of those numbers and divide by whichever value is the smaller value, right? That's just going to help us see what that magic ratio is. Cool. All right. So we're going to do another one here, and I want you all to get all the way to this step 3 for me. Okay, we're going to take another unknown compound. Where am I? So this one is going to be 36.85% nitrogen and 63.15% oxygen. What is the empirical formula? All right, and actually just for the sake of convenience, I'm going to take these 2 data points here, the percent by mass nitrogen and percent by mass oxygen. And I'm going to go back to my periodic table because, of course, we're going to need those molar masses to convert from grams to moles. Right, so again, the first step is to assume that we have 100 grams total, meaning there are 36.85 grams of nitrogen and 63.15 grams of oxygen. And then we're going to convert both of these to moles of each element using that molar mass. All right, so I'm going to kind of quietly start filling in the work up here. You guys continue to work on your own if you think you got the hang of it. If you think you're stuck, you can look up here for help. Okay, so I took my mass of my nitrogen, my 36.85 grams. I divided by my molar mass of nitrogen to get my moles, right? 2.6308. I did the same thing with oxygen. Took my mass of oxygen, divided it by the molar mass of oxygen to convert to moles. So now I have moles nitrogen and moles oxygen. But again, I can't say N 2.6, O 3.9. These have to be nice whole numbers. So again, in order to see that trick, what is the ratio between these numbers here? We're going to, again, divide by the smaller value. So I'm going to take my 2.6308 moles of nitrogen, divide it by the 2.6. That's my smallest of those two values. I'm going to do the same thing for my moles of oxygen, dividing it by that same 2.6 number. That'll definitely turn this into a 1. Any number divided by itself is just 1. Right? And when I do that 3.9 divided by the 2.6, I get a value of 1.5 moles, 1.5 moles of oxygen. Okay, so can I say NO 1.5? No, so I'm still not there yet, okay? So how am I going to make these both whole numbers here? I have one of them as a whole number, but this one still isn't a whole number yet, okay? So at this point, previously, in the previous problem we were done because they both worked out to be whole numbers at this point, all right? Now I have to do an extra step here, okay? What I'm going to do is I'm going to take both of those numbers and I'm going to start multiplying them by increasing whole numbers. Multiply them both by 2, see if that works out. Multiply them both by 3, see if that works out. Just keep on increasing, and eventually they will both work out to be a whole number, all right? So at this point, we're going to multiply by increasing whole numbers. And to be clear, by whole numbers, I mean 2, 3, 4, 5, 6, etc., etc. Okay, so if I take my two numbers here and I multiply them both by 2, right, 1 times 2, this will become 2 moles of nitrogen. And 1.5 times 2 Now all of a sudden that works out to be a nice whole number here, 3 moles of oxygen. Right? So now I get to be done my ratio here in my empirical formula, according to my mass spec data here, would be N2O3. If I didn't get whole numbers at this step here, I would just start increasing. Instead of multiplying them both by 2, I would multiply them both by 3. If that didn't work, I would multiply them both by 4, and I would just keep going until they worked out to be whole numbers. All right, in this case, after I multiply them both by 2, I get these nice whole numbers here. So that's my ratio of nitrogen atoms to oxygen atoms in my formula. All right, my empirical formula for my compound. So this, again, is what we would call the empirical formula. Okay, so from here, we could go one step further. Because again, this tells us the empirical formula of our compound, not the molecular formula of our compound, right? We got to this step here, the empirical formula. But what if I want to know how many carbons and hydrogens there are in this actual molecule? I'm going to need one other piece of information here. So now if I said the molar mass of this compound, and I gave you the specific molar mass, 152.0233 grams per mole. What is the molecular formula? Okay, now we could get lucky. Give me one second. We could get lucky, and our empirical formula could be our molecular formula. They could be the exact same. All right. So, but before we can figure that out, we got to check. So what are we going to do? We're going to calculate the molar mass of our empirical formula here. All right. So we're going to calculate molar mass of our empirical formula. And if they match, we're done. All right? So how are we going to calculate our molar mass from our empirical formula? Again, we're going to need what? Periodic table, right? We need those molar masses. Okay, so I'll bring that up again, move this over here. As always, you can see we love this periodic table. We're going to use it a whole bunch. Okay, so given this formula here, everybody take a second and calculate the molar mass. What was your question, sorry?
So when you were dividing by the smallest number, why did you not include the full number for oxygen, but you just left it as 1.5?
Because my calculator gave me 1.5000 and then like 2 something something. So that number was just super close to that 1.5. Yeah, and to be clear, I do always copy. I just like go up on my calculator and then copy it down because that's how you get the most accurate numbers, right? That'll take like, your calculator saves I think 20 decimal places in it or something like that. So that's always going to give you the most accurate number is going up and copying the number from your calculator. All right, so to be clear for my calculation here, I'm going to do 2 times the molar mass of nitrogen, which is this 14.00674 value, plus 3 times the molar mass of oxygen, this 15.9994 value. And that's how I'll get the molar mass of my compound here. Okay, so just to put it back over here, our molar mass of our empirical formula the N2O3 comes out to be 76.01168 grams per mole. Okay, so am I done? No, this doesn't match the molar mass of my compound. But remember, my empirical formula tells me whatever my molecular formula was, it just reduced to that there, right? So my molecular formula could be the N2O3. We nixed that out though because the molar mass doesn't match, right? Or it could be N4O6, multiplying both of those values by 2. But that ratio of 2 to 3 has to hold, right? Or it might be N3O9 or N4O12. It could be any one of these as long as the ratio between these two numbers is that same 2 to 3 ratio. Okay, so we could do it the long way where we went and then calculated the molar mass of this guy. Does that check out? No. Move on. Calculate the molar mass of this guy. Does that check out? No. Move on. Or we can make our lives a little bit simpler. We can take the molar mass of our molecular formula, okay, and divide it by the molar mass of your empirical formula. This will tell you how many of those little N2O3 building blocks you have in your molecule. Okay, so this is going to work out to some whole number here, N. So let's do this. Let's punch this into our calculator. And I get 1.99999, which is, of course, basically 2 here. All right, and so what this is telling me is in my molecule, I have 2 of those empirical formulas. So my molecular formula here would work out to be 2 times N for the number of nitrogens and 3 times N for the number of oxygens. Right? My empirical formula was the N2O3. So when I take my molar mass and divide it by the molar mass of my empirical formula, I get this whole number N. I'm going to update both of those subscripts by that value. So my molecular formula here, my molecular formula is the N4O6. Right? The N2O3 is what we called the empirical formula. We found the empirical formula from our mass spec data, and then using the molar mass of our compound, we were able to figure out what our actual molecular formula was. All right, so using that mass spec experiment, we have this unknown compound, we put it into this particular instrument, it gives us this mass spec data. We can do a little bit of math here to figure out what our compound's formula actually is. Okay, so the last thing we're going to do this week is we've been laying the groundwork here so that we can actually talk about chemistry. If we haven't even actually done any chemical reactions or talked about any chemical reactions, right? All we've been doing is kind of building our tool chest to be able to do so. And so next week's kind of an exciting week where we actually talk about chemical reactions, talk about what happens when we combine 2 different molecules together and what product we get, all right? We've had to build some groundwork here, putting formulas together, naming compounds, right? Building our vocabulary, learning how to do math, right? So we've kind of been like building up this tool chest. There's one more very important tool that we need in our tool chest so that we can really talk about chemical equations, and that's what's called balancing these equations. All right, so we're going to take a look at a chemical equation here, and you guys do not have to be able to see like, oh yes, I totally see how you got that product. You're just going to trust me. You're going to trust me that this is a reaction that happens out there in the wild. All right, so if you take CH4, this is a molecule called methane. It is very flammable. It reacts with oxygen gas, and these produce carbon dioxide and water. Okay? How did I know that? Because I just know that. Y'all are just trusting me, right? This is actually the same reaction that is occurring in your gas-powered vehicle as you're driving down the road. It's one of the reasons why we have a big CO2 problem on our hands right now with all the emissions that come from cars, because they're being powered by these chemical reactions that produce carbon dioxide as one of our products. Okay? So again, y'all are just trusting me. This is a reaction that happens here. All right? If we're going to look at the structure of these molecules here, and we're going to learn how to draw these figures at a future point in the course. For right now, you're just going to trust me that this is what these look like. A molecule of methane, CH4, has the carbon in the middle, and the 4 hydrogen molecules are bound to that carbon. Okay, so I'm going to keep track of my atoms here by coloring them different colors. I'm going to have the carbon be blue and my hydrogens be green. Okay, and this reacts with oxygen. Oxygen's actually got a double bond between it, but again, we'll get to that here in a second. Just focus on our number of atoms here. Okay? And this produces carbon dioxide. Again, you're just going to trust me on the structures here. Carbon dioxide has the carbon atom sitting in the middle, the 2 oxygens sticking off at the end. All right, and then water, we have the oxygen in the middle and the 2 hydrogens on the end. Okay, so these 2 molecules, are these combined together to form these here? On the left-hand side of our chemical equation, the methane and the oxygen, we call these the reactants because they're what react together. And on the right-hand side, we call these the products of our chemical reaction because they're what formed in our chemical reaction. Okay, but there's something wrong with this chemical equation as written here. Okay, and that is, it just doesn't work out that this 1 carbon atom with 1 carbon 4 hydrogen molecule turns into just 2 hydrogens over here on the product side. Or somehow I have these 2 oxygen atoms on my reactant side, but 3 on my product side. We got a balancing issue here. Okay? You can't just create atoms out of nothing. Atoms can't just disappear into nothing. That's not how matter works, right? So the same number of carbon atoms have to appear on the left as on the right. The same number of hydrogen atoms have to appear on the left and on the right. And the same number of oxygens have to appear on the left and on the right. That's what we call balancing our chemical equation. All right? So for this one here, it turns out that you would need 2 molecules of O2 to react in order to produce the correct number of products, which would be 1 molecule of carbon dioxide and 2 molecules of water. All right, now if we look at our balancing here, if I keep track of the number of carbons, I have 1 on each side. Oxygens, I have 4 on each side. and hydrogens, I have 4 on each side, right? So now my chemical reaction is balanced here. I haven't created any new atoms out of nothing. No atoms have disappeared. All right? Importantly, how this is going to appear in our chemical equation, I'm not going to change the formula of these compounds at all. What I'm going to do is I'm going to go and I'm going to update the coefficients out front here. So what I'm going to say is that for my reactants, right, we have 1 methane and 2 oxygens. So I'm going to say methane plus 2 oxygens, right? I'm going to put a coefficient out front of that 2 to indicate that there are 2 oxygen molecules in this reaction. All right, likewise, we said that we produced 2 waters in this reaction. So again, I'm not going to change the formula of water. I'm just going to update my coefficient out front here to indicate that there are 2 hydrogens. Okay? And this is called balancing a chemical equation. This is the name of the game, where this is the skill that we need to learn. And then we can start talking about what reactions happen out there in the wild. All right? Now, I drew these little pictures here to make a point. But when we balance a chemical equation, we don't actually have to draw anything. We just have to keep track of the numbers of each atoms that appear on both sides of our chemical equation. Okay? So let's do another one here. I'm going to give you an unbalanced chemical equation, and then we're going to work and balance this chemical equation. All right? So, turns out that sodium metal, and again, how do I know this? You're just going to trust me on this chemical reaction. But sodium metal, if we take sodium and we mix it with chlorine gas, we get sodium chloride. This is actually a little bit of a hilarious reaction because sodium metal is very dangerous to work with. It's very reactive with oxygen and will just like explode if it comes into contact with air. Chlorine gas is AKA mustard gas from World War I. Totally, totally toxic. You mix these two completely like explosive metal with this toxic gas together and you get what makes your food salty. All right, completely benign sodium chloride. Magic of chemistry. All right, anyways, this chemical equation as is not balanced. Right? If I go through and I look on both sides, my sodiums are actually balanced. I have 1 sodium on the left and 1 sodium on the right. But my chlorines, I have a problem. My formula for chlorine gas is Cl2. Okay? Meaning that there are 2 chlorine atoms in that molecule. And in my formula for sodium chloride, there's only 1, right? So again, my chemical equation is not balanced. I have a problem here. And I'm not going to touch these formulas at all. The Na, the Cl2, the NaCl, those don't get changed. The only thing I can do to my chemical equation is update the coefficients that are out front of each of these compounds. So what I'm going to do is I'm going to jump over to my right-hand side here and say, all right, I need 2 chlorines over there on the right. So I'm going to update this to a 2. Boom, now my chlorides are actually balanced. Now I have 2 chlorines on the right-hand side of my reaction here. But when I put that 2 out front of the NaCl, what did it also update over there on the right? The number of sodiums that I have, right? So now I have to change that as well. And now these are imbalanced. Ah, crap. Okay, so now I'm going to ping pong back onto the other side and update this to a 2. Okay? The pain in the butt thing about balancing a chemical equation is there's not like a one strategy fits all. You do steps A, B, C, and you always get the right answer. You got to guess and check. You got to ping pong back and forth. I'm going to update this. Okay, that changes something on this side. Okay, that changes something on this side. There's not a one-size-fits-all approach to it. You can actually break it down as a linear algebra problem, and it's like the most ridiculously complicated math problem you've ever seen in your life. All right, so we could formalize it, but it's not worth it. All right, we're going to do the guess and check here. Okay, so what you're going to do is you're going to count the number of atoms on both sides, And then you're going to update those coefficients to match. And you're just going to keep on ping-ponging back and forth between both sides until everything matches. All right, so let's do another one together. I'm going to give you a little bit of a head start on this one, and then we'll do it together here. All right, so aluminum oxide will decompose into just aluminum metal and oxygen gas. Okay, and again, just to be clear, you're going to trust me on these chemical equations right now. Next week, we're going to develop this whole logic behind what reactions occur. For right now, your goal is to take this unbalanced chemical equation and to balance it by adding those coefficients. All right, so step one, everybody take a second and tell me how many aluminums I have on both sides of this chemical equation and how many oxygens I have on both sides of this chemical equation. Okay, so how many aluminums are on the left? 2. And how many oxygens are on the left? 3. Oh, that's not a 3. Okay, how many aluminums are on the right? Just 1. And how many oxygens are on the right? 2. Okay, cool. So now my goal is to balance these out here. The aluminums would actually be pretty easy. I could stick a 2 out front here. That would update. But with my oxygens, I have this interesting problem here. There's no way for me to make a 3 into a 2 or a 2 into a 3, right? So these don't have any common factors here. What I'm going to have to do is turn them both into what's called their least common multiple in nerdy math speak, right? But I can turn these both into 6. I can take my oxygens and multiply it by 3. That will give me 6 oxygens over there. And I can take my aluminum and multiply it by, my aluminum oxide and multiply it by 2. And that will give me 6 oxygens over there. All right? So there's no way for me to make a 3 into a 2 or a 2 into a 3. So I got to make them both into this bigger number, into what's called their least common multiple. All right? Now, I just messed up my aluminums, though. Right? I have to make sure that when I updated that coefficient out front of my aluminum oxide, I changed this to 4 on my reactant side. All right, so now I have to go back. Again, it's a guess and check, right? So now I'm going to have to jump back and say, okay, no, I don't have 2 aluminums on the product side. I need 4 aluminums on the product side. And now everything's all balanced out, so I'm done. All right? But that's the name of the game here. We have to make it so we have the same number of each element on both sides of our chemical equation here. All right, so let's do another one here. Magnesium will react with oxygen gas to produce magnesium oxide. I'm going to count the number of magnesiums on both sides, count the number of oxygens on both sides, Okay, currently I have 1 magnesium and 2 oxygens on my reactant side, but I only have 1 of each on my product side. Okay, so in order to make my magnesiums match, in order to make my oxygens match, I got to put a coefficient of 2 out front of my magnesium oxide. But that also changes the number of magnesiums that I have, right? So then I got to fix that by jumping back to the other side and updating that coefficient out front of the Mg. All right, and now I have a balanced chemical equation. Okay? And what we're going to learn is these chemical equations are pretty useless unless they're balanced. Once they're balanced, we can actually use them to figure out how much magnesium oxide is formed in a reaction, et cetera, et cetera. All right, and that's what we'll be learning about next week.